Okay, so we've been doing surface area in these last couple of weeks, and what we're going to do now is we're going to be talking about what happens when you have two similar solids, two three-dimensional figures that are proportional, what happens to their surface area and volume. But before we can do that, we need to go back and pick up a lesson on just plain old perimeter and plain old area of similar figures. So it's been a minute since we talked about some similar stuff. That was like back in January. So let's go back and just remember what we're even talking about when I say the word congruent or similar. So we know the word congruent, that's the congruent symbol there. That's the squiggle over the equal sign. And that means two things have the same measure. They're the exact same size, exact same shape. Versus similar, we know means when those two shapes have congruent corresponding angles and their measures of corresponding sides are proportional. Remember what that really means, it's that they're the same shape but not necessarily the same size. They can be the same size, but if they're the same size, it's a one-to-one correspondence and we call that congruent. So if they're the same shape but two different sizes, we call that similar. So they have all their angles are congruent, their matchy-matchy angles are the same exact size, and their sides are what we call proportional. Remember what that meant is that meant that the ratio of their matchy-matchy sides reduced to the same amount. So 6 is to 3, as 6 is to 3, as 4 is to 2, all of these reduce to 2 is to 1. That's what it means to be proportional, is that their ratios all reduce to the same amount. So scale factor is just this reduced amount that we're talking about here. This is a 2-to-1 ratio. It's a 2-to-1 scale factor. 2 over 1 or 2 would be the scale factor. So, all right, so now we're ready to really talk about today's lesson, finding perimeter of similar figures. Okay, so we're gonna do this investigation here, but we're gonna do a little bit different take on it. You don't have any rectangles on a grid, so we're just gonna go with these two. We would have, if we were in class, we would have had some rectangles on a grid. So we're just gonna play along with red rectangle and blue rectangle. And let's tell you what, let's name this one the greatest of all time, and let's name this one troll. All right, so we have rectangle troll is going to be similar, so I'm going to do a squiggle, to rectangle goat. And so what that means is that this ratio, this 3-to-2 ratio, has to be the same ratio for all the sides in order for it to be proportional, right? So I have down here, we have 4 for the blue one, so we know in order for this ratio to hold, right, that it must be 6 over here for the matchy-matchy side on the red one. So what we're interested in today is not just the side length ratio, not just this 3-to-2 ratio. We already know how that works. What we are interested in today is what is the relationship between the perimeters of these two similar rectangles. So let's find the perimeter of a troll versus the perimeter of goat. So let's see, we've got 6 on the bottom, so we know on a rectangle opposite sides are congruent. The sides across from each other are congruent. 3 on the right, so we got 6 plus 6 plus 3 plus 3, that would be 18. And then on the goat, we've got 4 and 4 up top, 2 on the right, so 8 and 4 would be 12. So interesting if we do the troll to the goat perimeter ratio, 18 to 12, that reduces, let's see, 6 goes into 18 3 times and 6 goes into 12 2 times. Interesting situation here. What we see is that the ratio of the perimeters is it reduces to the same stinking ratio as the ratio of the original side-to-side ratio. And so that is our first theorem for today. So back to the note packet. Again, we're going to kind of skip over this little investigation, or at least the first half of it. So how does the similarity ratio of the rectangles themselves compare to the perimeter ratio? And so we know that the similarity ratio, what's called the side to side ratio, you're comparing the side length of one rectangle to the side length of the other, is equal to, it reduces to the same thing as the perimeter to perimeter ratio. And that's our first theorem for today, friends, is that it's called the proportional perimeters theorem. If a similarity ratio of two similar figures is A to B, then the ratio of their perimeters is also that same amount, A to B. So for example, if the ratio of these two rectangles is 8 to 2, or we can go ahead and reduce that to 4 to 1, I don't even have to find the perimeters to know that they'll be proportional and at what ratio. I automatically know the perimeters will have that same ratio.